All right, so you just heard about what reflections kind of look like, and we had this cool demo in Sketchpad. The question is like, what is Sketchpad technically doing to figure out exactly where to drop this image? There's a lot of geometric calculations going on. As I move this, it's happening really fast, actually. Here's the definition of what's really going on in reflection. Reflection line M. So M is the mirror line, and no coincidence they called it M. Maps every point P to a point P prime, such that, so here's the definition of how we know where exactly to place this. M is always the perpendicular bisector of the segment that would connect P to P prime. So when you set up that mirror line, if you look at this here, if you can imagine, oh, can I draw these in? This would be really slick. If you can imagine a point, or drawing from that point to, well, let me draw it right on here. Oh, it kind of does. You know what? I'm going to do this. I'm going to select all the points. I bet I could do this way. Sorry. Reflect. Okay, so now all the points are there. Oh, and look, it labeled them as primes and all that stuff. Okay, so if I was going to draw this segment from here to here, or from here to here, notice every time I connect an image point with its pre-image point, I get points. I get all those little connections, from those black lines, essentially. They have this pink thing as their perpendicular bisector. It's going to stay perpendicular all the time. And this line is going to contain all those midpoints. And that's just the way reflections are defined. That's for any point off the line. So if P is not on the line, you do that. You make it so you kind of start heading perpendicularly towards the line. You get there, you're halfway there. You keep going. And then when you've gone that same distance on the other side of the line or kind of behind the mirror, you can stop. That defines it for almost all the cases, but what happens if your nose is right on the mirror? What do you do? Well, then it actually doesn't move. If the point is on the mirror line, it doesn't move at all. I can show you that if I move this right here. Notice that point at the top there. The definition of reflection is, well, if it's on the mirror, it doesn't move at all. Otherwise, it does this perpendicular bisector kind of idea. To write this out in notation, we use capital R. Here we go. Capital R stands for reflection. So before we were using crazy names for stuff like mapping G in general, blah, blah, blah. Well, if they use an R, that's not generic anymore. R is designated for reflections, particularly when you see R with a little subscript down here. So R here, just the big R in general, stands for the word reflection. You can be sure it's a reflection if they use the word R. The little M down here, because if you're going to do a reflection, you have to say which mirror you're talking about, because there might be more than one reflection in one diagram or in one problem. So this is the line of reflection. So the big R just tells us that we are talking about reflections. M kind of tells us, well, which reflection do you mean? You mean the reflection in M. So we might have stuff later, well, you'll see it today. We're going to have stuff like big capital R, small subscript down here, line N. Or big capital R, small subscript down here, the y-axis on the coordinate graph. So this has to be the line down here. And what this is saying is, okay, if I read the rest of this, the reflection over line M will take point P and map it to point P prime. Or you could write it this way too, with this is arrow notation, this is the equation notation. You should have done this kind of stuff in algebra using either the arrows or the equals. That's just saying P went to P prime when I reflected it over M. The reflection of P over M is P prime. Rewind that and watch that again. That's a good way to say that. The reflection over line M takes point P to point P prime. That's just saying this is what this is actually happening here. All right. There's another word here. I don't think it's a terribly important vocab word, but since S didn't move under this reflection, we say it's invariant. It's like when you multiply things by 1, they don't really change. It's like, well, we tried to move it and it didn't move. So is what we call invariant. That was an invariant point. Any point on the lines would be invariant. All right, here's some with coordinates. Believe it or not, again, I think these are sometimes easier. Common lines of reflection would be reflection in the x-axis. You could write that this way, big capital R, little tiny x-axis in the subscript. That would be how you'd see that. Why is this not writing for me? Reflection on the y-axis. So it would look like this. You might see this on a test. That's how you write that. Sorry, it's so small. And reflection of the line y equals x. Yeah, believe it or not, you can actually put an equation in the subscript. And that means that's the line you use for reflection. And these are on here because, again, they are very common. So they have the blue ones here are always the pre-image. We're starting from some generic point xy. When you reflect over the x-axis, think about what's going to happen. So again, we're traveling to figure out, like, okay, this is the mirror, this red line. Here's your nose. Here's the nose in Wonderland, right? Here's the nose in the mirror. To figure out exactly where this point goes, you start moving perpendicularly towards the mirror, right? That was supposed to be perpendicular. Then you keep going so that the distance you've gone inside the mirror equals the distance you had to go to get to the mirror, so that this becomes the perpendicular bisector. They did the same thing here, but now we're using this mirror, totally different mirror. Move towards the mirror perpendicular, keep going, same distance on the other side, so that this segment connects in such a way that the red line's a perpendicular bisector. This is a little harder to see, but this is also what's going on here. This point, go perpendicular towards the mirror, keep going just as far. You'll find the image. That's how those were located. Okay, isn't this fun? This is like my favorite unit of the year. If you can't tell, like, this is awesome. And this study, this geometric transformations thing, not only is it the geometry of motion and, video games and marching band formations, like this is how they plan stuff out. And it's kind of snazzy and animated on the computer. It is so much newer than all the geometry we've studied all year. All the geometry we've studied all year was known by Euclid like 3,000 years ago. This is like 20th century at least. So this is way more interesting, I think. And it requires so much more technology, or it's got so many more applications of technology. It just makes it so much more relevant. Thanks for putting up with the rest of the year, but this is where it gets a little bit more relevant to something you might see yourself using in the future. So thank you for getting this far. All right, finally label the image of this point and of this triangle under the reflection. So I just have this one on this page. On the next page I have another. So we're going to reflect this over the line y equals x. So here's our mirror. That would be the red line from the last page. So I'm going to reflect. That's a horrible highlighting, by the way. I'll do that better. I'll highlight it this way. So if this is the reflection line, it's a lot better. Now it's somewhat better. There's our reflection line. Actually, you know what? You can see it now. I don't even have to draw that anymore. You know where we're talking about. Reflect the point 2, 4 over there. All right, so reflect the point 2 over there. Again, this is the mirror. We're going to go perpendicularly towards the mirror. So that was a segment of 4. Keep going on the other side. It's going to have to be right there. Where are we? Oh, we're at 2, -4. Oh, by the way, it talked about that in the last page. In general, the point xy is going to go to the point x comma -y. The x-coordinate, notice, would stay the same. Y's just go that much farther on the other side. Y was the height here, so we're going to go that height underground. And this will work no matter which quadrant we start in. Reflecting over the x-axis, look at what happens. Y-coordinates stay the same. We stay at the same height, but the x-coordinate flip-flop, positive, negative. This one, you might not be able to predict this, but look what actually happens here. What happens here is any point xy is going to have to flip around so that the old x-coordinate becomes the new y-coordinate and vice versa. So this point was, it looks like it's about -7, 2 or something like that. This would be 2, -7. When you flip coordinates around, that's exactly what you do. You end up getting the point that would be the reflection across the line y equals x, which is just kind of a cool feature of geometry. There's a lot of hidden treasures like that all over this unit, and Algebra 2. So get ready for that. That story's not over. All right, flip this over the same axis. Well, B is going to go right there. You can probably tell that by... Oh, yeah, I should label this P prime, shouldn't I? A is going to go right here. That's lovely. C is a little hard to tell, so it's going to stay on this street. But it's going to go, how many is this? 1, 2, 3, 4, 5, 6. I got to keep going 6. 1, 2, 3, 4, 5, 6. So let's look about there. What they haven't told you yet, or what I have failed to mention, I guess, is, okay, that's where point A goes. That's where point B goes. That's where point C goes. But guess what? This entire triangle still has to connect all the same dots. So the way to reflect something like a triangle is you reflect all the important points, enough points you need, as many points as you need to be able to reconstruct the picture on the other side. And guess what? Yeah, the connection from B prime to C prime is a reflection of the connection from B to C, and et cetera. So they're all like that. I have a note about this one here. Notice if you think about if you were to call this triangle ABC like we did, the label, the decision to label it A to B to C, A to B to C, that was kind of a clockwise naming system. Then if we figure out that that thing maps to triangle A prime, B prime, C prime, look at the way A prime to B prime to C prime is labeled. the labels A prime to B prime to C prime kind of go that way. That's a counterclockwise labeling system, or this was a clockwise labeling system. That's a really quick and, I don't know, mathematically definable way to say, you know what, this one's really backwards from this one. You look at two triangles, or you even look at two squares or something like that, and you go, okay, did this really flip it over? Is it backwards? I can't really tell. Here's the way to always tell. Look at the labeling system. This label system ABC was clockwise. That would correspond to, just put primes on the same letters in the same order. A prime to B prime to C prime, that's going the other way around the figure. So that's definitely reversed. 1 point to 1 point, that figure didn't have any orientation in the first place. This point P and this point P prime. So you don't really talk about orientation of a point, or really even orientation of a segment, but you get to polygons and things, then yeah, there's an orientation there. There's a 3-point labeling system. And if I follow the same order of points, but just compare the originals to the primes, they go in opposite directions. And I could have called this CAB in first place and go, oh yeah, CAB, that would have been clockwise also, or maybe even CBA. Oh, that would have been counterclockwise. But you compare CBA to C prime, B prime, A prime, they're going to be opposite directions if you keep the letters in the same labeling order. So that might have been too technical. It may be easier to see than what I just explained there. But if you get stuck again, come back to that one. All right, same thing. New. I'm going to cheat now. New line. So the line here now is actually over this y equals x line, which is kind of this direction. Oh, this is lovely. I mean, for it to be black, but it's kind of around here. That's not really straight, but it goes along those types of streets. How are we going to get that perfect, or how are we going to figure out those coordinates? Well, remember the rule back here from the y equals x stuff. If it's y equals x, you just reverse the coordinates. xy becomes yx. It's like that Bizarro world thing from Superman. So 2, 4 is supposed to go to 4, 2. I mean, you could get really technical with a ruler and a protractor and go perpendicular and all that stuff, but you can kind of just look at this and go, hey, that's one diagonal square. Of course, my black line's a little bit off. And one diagonal square, keep going. Yeah, that's perpendicular, so yeah, sure, I can kind of believe that. 2, 4, 4, 2, perfect. B was at -2, -1, so it should go, again, my black line's a little bit off. It's going to go there. A was at negative, what is that, 6? And -1, so it's going to be down here at -6. Because I'm just going to reverse the coordinates. So that's B prime. This is A prime. C, I think it's going to go right there. I'm just trusting my line here, but this is 5 this way and 5 that way. No, can't be. 1, 2. Did I miss that point? Wait a second. 2, 4, 5. 2, 4, 6. Okay, so it's 5 this way and 6 down there. Originally, I'll label this one because this was tricky. This was -5 and -6. This is going to end up C prime is at -6, -5. Okay, and then connect the dots as you would. How come I couldn't get this to work out nicely? Maybe this will work. Oh yeah, my cheater ruler is working nicely now. Okay, my black line's a little bit off, but not too bad, actually. Okay. What's the effect of slope on a line? What's the effect of reflection on slope of a line? So if you look at the slope of a line, and then you reflect that line somehow, and then you see what happened to the slope of that. We've already talked about distance, and how distance might be affected by doing various transformations, and if you forgot, notice that the distances in all these segments are the same as all of those. The distances, same triangle here, are the distance same as distances here. Remember, reflections were congruence transformations or isometries. So these triangles not only, they're side congruent. So don't worry about distance with reflections. Reflections keep distance the same. But what about slope? I'm going to save that question for part 3, which will be very short, but I'm not going to be able to finish it in part 2.